and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler, and today we'll be doing Unit 7, Lesson 6 on Reasoning with Similarity. So now we get into the proof portion of Unit 7, where we're going to look at how we can prove triangles are similar, and then what we can do with that, how we can extend those proofs a little bit further. For now, let's just jump into that first basic issue, right? Proving two triangles are similar. Just as we were able to prove two triangles are congruent, we can also prove two triangles are similar using the angle-angle theorem for similarity, or the side-angle-side theorem, or the side-side-side theorem for similarity. Of these three, make no doubt about it, the angle-angle method is most commonly used. So, let's take a look at exercise number 1. Given that AB is parallel to DE, and segment AE intersects segment BD at C, prove that triangle ABC is similar to triangle EDC. Now, there's a few ways to do this, all right? But let's just kind of understand what we can tell from the givens, all right? First off, we know, right, that AB is parallel to DE, all right? And that tells us quite a bit, right? Number one, we could say that angle A is congruent to angle E because they're alternate interior angles. Angle D would have to be congruent to angle B because they're alternate interior angles. And if you didn't want to use one of those two pairs, you could also claim that angle ACB is congruent to angle DCB, not because they're alternate interior angles, but because they're vertical angles. Anyhow, it doesn't matter which two pairs of angles you use, you're going to get the angle-angle similarity theorem. So, pause the video now, and well, actually don't pause the video. This is our first similarity proof. Maybe we should do this one together, right? So let's get it down. I'm going to say AB is parallel to DE. Simple enough, my given. I also want to get down my other given, AE intersects BD at C. That's also a given. This one really allows us to conclude those vertical angles. Without this given, we wouldn't necessarily be able to know that AE and BD were straight line segments. This implies that. Now, let's get angle BAC congruent to angle DEC. That's this angle pair and this angle pair. And if I had said angle A is congruent to angle E, that would also be okay. We wouldn't have to use the three-letter naming system. That's just alternate interior angles formed by parallel lines are congruent. I think now I'm going to get that vertical angle pair in. Again, you could do the other alternate interior angle pair and it wouldn't make a difference. That's often the case in similarity proofs, but that's just because vertical angles are congruent. So ACB is congruent to ECD, vertical angles are congruent. And finally, triangle ABC is similar to triangle EDC, and that's the angle-angle similarity theorem. All right, piece of cake, easy. Pause the video now and write down any of these statements or reasons that you need to, keeping in mind that instead of using this vertical angle pair, you could have also used the other alternate interior angle pair, and that would have been fine as well. Take a moment now to write down anything you need to. All right, now let's take a look at exercise 2. State an extended equality that shows how the three corresponding pairs of sides would be proportional to one another from the diagram above. All right, now this is really critical because right now what we know is that this small triangle up here is similar to this larger triangle down there, okay? And I want to be able to say, oh, this side divided by this side is congruent to this, is equal to this side divided by this side, etc. That can be a little bit tricky, especially when the triangles are oriented this way. Now keep in mind, right, what we knew was that this was congruent to this angle was congruent to this, and then those two vertical angles. So one thing that might be helpful to write this down is to redraw triangle ABC below the other triangle in an orientation that is the same. All right, so in other words, I'm going to take this triangle. I actually have to rotate it 180 degrees and draw it down here. But now I've kind of drawn it so that it has the same shape. I can really see it, right? And now it's easy enough. Now, I could start here and do this divided by this, or I could start up here and do this divided by this. I think I'm going to start down here and I'm going to say that AB divided by ED, so AB divided by ED, okay, is equal to AC divided by EC, and that's equal to BC divided by DC. By the way, that's what we mean by an extended equality. So most of the time, if I just say write down an equality, I'm talking about writing something like that down. This is an extended equality, which means this ratio is equal to this ratio, which is equal to this ratio, which means this ratio is also equal to that ratio, etc., right? Any side length on the small triangle divided by the corresponding side length on the larger triangle has to be equal. That is what we mean when we say corresponding sides of similar triangles are proportional or in proportion. All right, let's keep going. Now, it is often the case when trying to prove two triangles are similar, we simply have to find two pairs of congruent angles that are contained in the two triangles, right? That whole angle-angle similarity idea. Let's take a look in exercise 3. In the diagram shown, segment MN is congruent to segment MP. Points R, S, T, and W all lie on the sides of triangle MNP, such that RT is perpendicular to NP and SW is perpendicular to NP. Letter A. Explain why triangle NTR must be similar to triangle PWS. All right, so again, I'm trying to explain why this particular triangle, maybe I'll outline them, right? This particular triangle is similar to this particular triangle. Okay. Well, I'd like you to pause the video and see if you can figure out, think about why these two triangles have to be similar, and hone in on that whole, the whole idea of having the angle-angle similarity theorem. All right, well, there's a few things. In fact, there's two things, right? At least that's what I'm pretty sure of, right? One thing right away is the fact that MN is congruent to NP, right? Which makes the large triangle MNP an isosceles triangle. And because it's an isosceles triangle, the base angles of that triangle must be congruent, right? Now the other piece, RT is perpendicular to NP, all right, and SW is perpendicular to NP. That means that this has got to be a right angle, and that's got to be a right angle. And therefore, I've got two angles in this triangle that are congruent to two angles in that triangle, and therefore the two triangles have to be similar by the angle-angle similarity theorem. All right, let's get that down. So first I'm going to say angle N must be congruent to angle P, because base angles of an isosceles triangle are congruent. All right, and I can say that angle T, oh no, I can't call it angle T. That's terrible. Angle NTR is congruent to angle PWS because both are right angles. So triangle NTR must be similar to triangle PWS by angle-angle. All right, and it's kind of cool, right? Because one pair of angles came from the fact that they were base angles of an isosceles triangle, and the other pair came from the fact that these two lines were drawn perpendicular to that base of that isosceles triangle. All right, great. So now let's do a little bit of algebra. Letter B. If RT is equal to 12 and PW is equal to 3 and SW equals NT, then solve for the length of SW. All right, cool. Now remember, what I've got is these two similar triangles and nothing else particularly matters. So let's like write some things down, right? We have RT is equal to 12, and we've got PW is equal to 3, and SW is equal to NT. So I don't know, maybe I'll call them both X, right? Okay. Now I want to figure out the length of SW, so I need to figure out S. Now what I know, right, from my extended equality is that RT divided by SW will be equal to NT divided by PW. Again, make sure that you understand that, right? This length divided by the corresponding length over here will be equal to this length divided by the corresponding length over here. So RT divided by SW is equal to NT divided by PW. Let's now fill in the blanks, right? RT is 12, SW is X, NT is X, and PW is 3. Okay, simple enough. This one we're definitely going to want to cross multiply on. So I cross multiply X times X is equal to 3 times 12. X times X, as we all know, is X squared, and 3 times 12 is 36. And I take the square root of both sides. Even though I get plus or minus 6, I'm only going to have positive 6 because these are lengths. They can't be negative. There it is, right? And by the way, just for a second, if I put a 6 in here and a 6 in here, it makes a lot of sense, right? Because here we have 12 is double 6, and 6 is double 3, right? So the sides of this are twice as big as the sides of that. One of them is just twice the size of the other. All right. Now sometimes, it's rare, but sometimes a set of similarity criteria other than angle will be used. It's rare, but it can happen. Let's take a look in exercise 4 at a classic situation. In the diagram shown, points B and C are midpoints of sides AE and AB respectively. Excuse me. They have been connected to form segment BC. Draw sketches of triangle ABC and triangle ADE separately below. All right, so why don't you go ahead and do that. Draw those two triangles separately down here. Okay. Well, what I have is just my two triangles immediately. You don't want to have to look at my ugly looking drawing anyway, so there they are, right? I've got triangle ADE and triangle ABC. Okay, cool. Now let's look at letter B. What angle must be congruent between the two triangles and why? All right. This should be pretty easy, but pause the video right now and tell me what angle must be congruent between the two triangles. And maybe I should have said what angle pair, because by saying what angle, maybe I gave it away. It's got to be angle A, right? Because it is literally a shared angle, right? Now maybe I'll call it this. I'll say angle EAD must be congruent to angle CAB because they are, I'm going to say a shared angle. A shared angle. Right? They're literally this angle right here. Right? That angle is the same angle. But that is the only angle that we know for certain, just based on what we've been told, is equal. So we don't have enough right now to use angle, right? I don't have any other angle pair. That's it. Letter C. Why can we use the side angle side criteria to conclude that these two triangles are similar? So I claim we can use side angle side. Pause the video right now and see if you can figure out why. All right, well, it's kind of cool. Remember what the side angle side theorem says. It says if I've got two pairs of sides that are proportional and the angle in between them is congruent, then I can use the side angle side criteria to conclude that the two triangles are similar. Well, keep in mind, right, that C and B aren't any random points on these sides. C and B are the midpoints of AE and AD respectively. So what I know right now is that AE divided by AC has to be 2, and AD divided by AB must be 2 because of those midpoints. Because B and C are midpoints, right? And since angle A lies between these two pairs, we can use, whoops, I almost said side angle again, side angle side. Right? It's rare, but I know, right, that I've got these two sets of side pairs that are proportional to one another. They're both have proportions equal to 2, right? And then, because the angle in between them is the angle that I know is equal between the two triangles, then I can say that they must be similar using side angle side. I could literally dilate the smaller triangle with a center at A, right, and a scale factor of 2, and it would stretch that smaller triangle so that it mapped on top of the larger triangle. All right. Letter D. Given that triangle ABC is similar to triangle ADE, why must angle EDA be congruent to angle CBA? And then let's not worry about the rest of it for right now. We'll get to that. So based on the fact that the smaller triangle is similar to the larger triangle, why can I say now that EDA, which is right here, must be congruent to CBA? Pause the video now and see if you can answer that question. Well, it's very simple. Corresponding angle pairs in two similar triangles are congruent, right? These angles correspond, or these are corresponding angles which in similar triangles are congruent. Now to the second part of this. What does this congruence tell you about segment ED and segment CBY? So if you didn't know anything about similarity or anything like that, and I just gave you this picture and I said this angle is congruent to this angle, what could you then say about ED and CB? Well, not surprisingly, you could say that they're parallel to one another, right? They're parallel to one another. So ED is parallel to CB because, right, a corresponding pair of angles is congruent. Now, before we move on to the next slide, I just want to give a little nod to a lesson that we did in the last unit. In the last unit, we had a lesson called the midpoints of the sides of a triangle. And in that particular lesson, we said if you connected the two midpoints of any two sides of a triangle, the resulting segment length that you had, or the resulting segment that you got, would be parallel to and half the length of the third side. Now, the fact that this one is parallel to this one, we just sort of proved here. And the fact that this is half the length of this, would come from the fact that that final set of sides, right, must be proportional just like the other two sides are. And since these longer sides are twice the length of these shorter ones, that would mean that ED would have to be twice the length of BC, or, right, BC would have to be half the length of DE. So we're getting exactly the same result, except looking at it from the lens of similarity. Okay, one last problem. Exercise number 5. In the diagram below, parallelogram ABCD has point P located on side CD. Segments AP and BC are extended to point M where they intersect. Give an argument for why triangle MCP must be similar to both triangle ADP and triangle MBA. Wow. Okay. Well, it's important to just understand where all the relative triangles are here, okay? And to understand that we've got a parallelogram. So I'd like you to pause the video right now and really think about it. And I would do it one in a turn. Like first, why is triangle MCP similar to triangle ADP? And then why would triangle MCP be similar to triangle MBA? And we'll take them both in turn, but pause the video now and see if you can at least think about why that one triangle must be similar to both of those other two. And by the way, of course, if this triangle is similar to both of these two, then by default, these two would have to be similar to each other because they all have to have the same angles. All right, well first, let's talk about these two particular triangles, MCP and ADP. One thing that you have to remember always, is that in a parallelogram, right, side lengths or sides are parallel to each other. So the fact that ABCD is a parallelogram tells us a ton, right? And one thing that I can say for certain, right, is because AD is parallel to BM, I can definitely say that this angle and this angle are congruent because they are alternate interior angles. In fact, let me get that down, right? Because AD is parallel to BM, angle ADP is congruent to angle CMP because they are alternate interior angles. Awesome. Now remember, I'm always kind of shooting for the angle-angle similarity theorem, okay? So where do I get my other angle? Well, I could get my other angle in one of two ways. I think the easiest way is grabbing that pair of vertical angles right there. But again, because AD is parallel to BM, you could also claim that this particular angle here is congruent to that particular angle there because they're also alternate interior angles. But I'm going for the low-hanging fruit, as we like to say, and I'm going to grab my vertical angle pair. I'm going to go with these two. So angle APD must be congruent to angle CPM because, excuse me, they are vertical angles. So triangle MCP is similar to triangle ADP by angle. Ah, the red's just coming out all over the place. All right, so we've now got this triangle similar to that one. Now I'd like to try to get this triangle similar to this larger one. And that's definitely a case, if I kind of wipe that out, this one is definitely a situation, right, where I've got that smaller triangle kind of embedded in a larger triangle. All right, let me get rid of these to help myself out. Now again, there's many ways to do this, okay? One way to do it again is by noting that I've got a parallel line here and a parallel line here. And because those two lines are parallel, this angle would have to be congruent to that angle, not because they are alternate interior angles, but because they are corresponding angles. Likewise, I could say this angle is congruent to that angle because, again, they are corresponding angles. If I wanted to, I could even say angle M is congruent to itself, right? Because it's a shared angle between MCP and MBA. I think I'm just going to grab the two I've marked since I already have it. So I'm going to say, since AB is parallel to DC, I can say that angle MCP is congruent to angle MBA, and angle MPC is congruent to angle MAB because they are corresponding angles created by parallel lines. So, triangle MCP is similar to triangle MBA by angle again. Okay, now I don't know if you've noticed this, but many times when you prove that two triangles are similar by the angle-angle similarity theorem, it's actually possible to prove angle-angle-angle, right? So I could have easily done that in the second case. I could have said M is congruent to M, this one's congruent to that one, this one's congruent to that one. That's because of the parallel line business, right? So one of the things that can be tricky for students when they use angle-angle is that you only have to get two pairs of congruent angles. And a lot of times that third pair is also there, and it's like, well, but what about that one, right? Well, you just don't need it, right? You could use it, but you don't need it. And it all just depends on which angles you want to use. That was actually the case in both of these situations. In the first case, I used an alternate interior angle pair and a vertical angle pair, but I could have used two alternate interior angle pairs. In the second case, I used two corresponding angle pairs. All right, so let's wrap this up. All right, we are going to be doing more proof in the next lesson, and of course you're going to have some proof on the homework where we're trying to prove that two triangles are similar. The vast majority of time when you do that, you simply need to use the angle-angle similarity theorem and establish that two angles in one triangle are congruent to two angles in another triangle, which then makes the two triangles similar. It could be on occasion that you use the side-angle-side similarity theorem, like what we saw with that midpoint problem. It's extremely difficult actually to come up with a proof where you use the side-side-side theorem for similarity, because in that case often you have to pretty much know numerical lengths of sides, which we rarely do in a proof context. All right? So first and foremost, when you're trying to prove that two triangles are similar, look for congruent, right? Look for angle-angle, all right? Very important. All right, for now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.